Models usually address the needs of particular applications and they are designed for them. However, the experience from many similar applications in a domain and the general knowledge of a domain can be captured in a more general, let me call it so, model that could be used as a guide for building specific application models and for exercising good practice in doing that. Such models are called ontologies, and I'd like to turn to ontologies now. Models are usually targeted at one or more specific applications within a given domain, and they underlie the development of information systems for these applications. For example, library management systems, museum documentation systems, bank information systems, e-commerce systems, etc. By abstracting out from such a set of models in the same domain, we can arrive at a conceptual model that captures our general perception of the possible states of affairs in a domain of discourse, disregarding the particularities and conventions of specific application environments. This model should comprise only classes and properties of inherent significance for the understanding of the domain, formally defined. Such a model is called an ontology. The term is borrowed from the name of the branch of philosophy dealing with the study of the nature and categories of being. In the information sciences, on the other hand, an ontology is an artifact. It is a model that formally defines the classes and properties of the entities that fundamentally exist in a domain of discourse, thus serving as a knowledge organization system concerning that domain. Depending on their scope, ontologies are distinguished into upper or general ontologies, which deal with general ubiquitous notions such as object, place, time, activity, location, composition, order, etc., and domain ontologies, dealing with the basic notions of a given domain, yet not the specifics of any particular application. A prominent example of an empirically based, inductively developed ontology for the cultural domain is the CIDOC CRM, developed and maintained by a special working group of the Documentation Committee of the International Council of Museums and an ISO standard since 2006. It results from the understanding of many existing models and is the outcome of long-term interdisciplinary work and agreement. The CIDOC CRM describes the underlying semantics of data schemata and structures of all museum disciplines and archives. The CIDOC CRM is what we call an event-centric model. A key feature of the CIDOC CRM is the distinction of all entities into persistent and temporal. Persistent are entities that exist in their entirety at any instant in their lifetime. So people, objects, ideas, and concepts are considered to be persistent entities. For example, my cat, the marathon, the Parthenon frieze are persistent entities because at any point in time that they exist as a whole. Temporal entities, on the other hand, only exist in part at any instant in their lifetime. They are events and activities that evolve in time, say the Battle of Marathon or the making of the Parthenon frieze, and at any instant in time, it is only part of that activity that has already evolved and can be observed. Persistent entities are initiators, recipients, or witnesses of events and activities, and they also originate or terminate in events, or they survive events. The general idea behind CIDOC CRM is captured in this simple figure. Temporal entities represent events and activities, and the history of any object or other entity we may want to record is a series of events and activities. Each event or activity has its limits in space and in time, so we have time and spatial coordinates, and in each activity actors participate in different roles, and physical entities and conceptual objects affect or are being affected by those temporal entities. There's a naming system captured by the entity appellations shown there, which allows us to assign names to all the real-world items of interest, and there is a system of types that allows to categorize or to characterize real-world items in different categories. Now, CIDOC CRM comprises about 90 something entities, classes of entities, and about 150 properties. But these properties fall in a few large kinds of properties or types of relations. So the general types of relations in CIDOC CRM are identification relations, that is, relations we use in order to identify real-world items by calling them by real-world names, classification relations that allow characterizing and categorizing real-world items. The type system is such a medium. Composition relations, or otherwise called part-whole relations, and these apply to conceptual objects, physical objects, periods, actors, places, everything. There are relations that denote the participation of persistent items in temporal entities, and this makes it possible to create a notion of history. Location relations that allow to determine the space-time bounds of physical objects. And finally, relations of influence of objects on activities and relations of reference of information objects to real-world items. We shall now take a look at the specialization hierarchy of temporal entity. The class temporal entity comprises all phenomena which happen over a bounded extent of time. It is specialized into period and condition state. Condition state comprises the states of objects characterized by a certain condition over a time span. For example, a building laying in ruins in a certain period of time. Period, on the other hand, comprises sets of coherent phenomena or cultural manifestations bounded in space and time. It is the social or physical coherence of these phenomena, however, that identifies a period rather than the associated bounds in space and time. For example, the Pliocene or the Jurassic period, World War II, Impressionism are periods. Event is a subclass of period and comprises phenomena that change the state in cultural, social, or physical systems. Such changes of state affect instances of persistent item or its subclasses. The distinction between an event and a period is partly a question of the scale of observation. Examples of event are my birth, the Battle of Waterloo, the eruption of Vesuvius. Activity is subclass of event and comprises actions that are intentionally carried out by instances of actor. This notion includes complex, long actions, such as the building of a settlement or a war, as well as simple, short actions, such as the opening of a door. Examples of activity are laying the foundations of my house, the composition of Carmen by Bizet, the naming of a street by the Municipal Council of Athens. Now let's see how a particular subclass of activity may be exploited in order to express a kind of activity that is of particular interest. In the case of our example, the action of assigning an attribute of some kind, characterization of some kind, is considered an activity, and in CIDOC CRM it is the class attribute assignment, which is assigning some CRM entity to another CRM entity. A particular subclass of attribute assignment is the class measurement. Measurement represents the actions of measuring something, that is, measuring an instance of the class thing, and the outcome of measurement is some dimension of that thing, comprising two elements, a number and a unit of measurement. Now, we record measurements as instances of the activity measurement in cases that we want to have a recording of the activity itself. Because measurement is a subclass of activity, we can record the actor of this activity and the place where it was carried out, the instruments by which the measurement was made, and so on and so forth, so we can have a full recording of whatever took place that had this particular measurement as the outcome. On the other hand, we may be interested in just assigning a dimension attribute to the thing in order to show the outcome of the measurement, in which case we are not interested in the act of measurement itself. So we have two flavors of measurement here, measurement as an activity and measurement as the outcome of that activity. And the two are reconciled, as you see in this model, and the direct path from thing to dimension is considered as a shortcut in CIDOC CRM. This is a phenomenon that occurs in many other situations where we have an activity with some outcome, but also the outcome is attributed directly to the thing affected by the activity. For more on CIDOC CRM, including the model itself, implementations, tutorials, use cases, publications, mappings, etc., you can visit the CIDOC CRM webpage. Ontologies are designed to be understood by both people and machines, so they support developing a common set of concepts and a nomenclature for a domain, as well as indexing of content and automated reasoning. Very importantly, an ontology should not mandate documentation fields or values. Rather, it should only define the intended meaning of classes and properties. It therefore can accommodate local terminologies of different systems, and it supports the transformation and the linking of data between systems, provided that their schemata can be mapped to the ontology. Thus, the ontology is an enabler of uniform data access, data linking, and system interoperability. The ontology can also serve as the basis for common good data representation practice by encouraging the development of specific application models by specializing and extending the core model provided by the ontology. The CIDOC CRM is an example of an ontology that has the above required qualities.